Welcome. My name is Austin Kohler, and I will be presenting our research on the linearized rigid body static and dynamic stability of an aircraft with a bio-inspired rotating empennage. I will first introduce the project this research is a part of. It is expected that next-generation fighter aircraft will lack a vertical stabilizer. The Bio-Inspired Rotating Empennage, or BIRE, could satisfy this design goal. The BIRE aims to provide lateral control by rotating the horizontal stabilizer about the fuselage axis in a way that replicates a bird's rotating tail. The objectives of this research as it pertains to the overall BIRE project are as follows. 1. Identify how modifying a fighter aircraft with the BIRE affects its static stability, dynamic stability, and handling qualities. 2. Quantify these effects for an example fighter aircraft. Establishing a fighter aircraft model is a prerequisite to accomplishing these objectives. The baseline fighter aircraft is based on open NASA data for the General Dynamics F-16 Fighting Falcon. The BIRE stability effects can be determined by comparing the unmodified baseline aircraft to a BIRE-modified version of that aircraft. An aerodynamic model, detailed in this research's companion work, is created using the physical model and modern lifting line software. Both aircraft's aerodynamic models can then be used to quantify the BIRE's effect on the baseline's static stability. Static stability about the three rotation axes is determined using the sign of the aerodynamic stability derivatives. The results of these comparisons are as follows. Plotting the pitch stability derivative as a function of BIRE fuselage rotation angle suggests that the addition of the BIRE decreases the baseline static pitch stability outside of BIRE rotation angles of plus or minus 6 degrees. Similarly, the roll stability plot suggests that the BIRE decreases the baseline static roll stability, but not enough to make the aircraft fully unstable in roll. The yaw stability plot suggests that the BIRE also decreases the baseline's static yaw stability to unstable levels within BIRE rotation angles of plus or minus 14 degrees. The dynamic stability analysis seeks to quantify the dynamic response of each aircraft to disturbances. The following slides outline the coupled dynamic stability eigensystem derivation, which constitutes a major section of this research effort and is vital in analyzing each aircraft's dynamic stability. Calculating each aircraft's dynamic stability begins with the general, coupled, 6-degree of freedom dynamic equations of motion for asymmetric aircraft. These nonlinear equations are then linearized about an equilibrium flight condition, which for this research is steady turning flight. This equilibrium condition allows both steady level flight and steady coordinated turns to be studied. Assumptions derived from the equilibrium condition are then used to determine the linearization's equilibrium values. Similar assumptions can be used to simplify some of the force and moment derivative terms. The linearization and simplification process results in a general coupled eigensystem for asymmetric aircraft that can be used to analyze each aircraft's dynamic stability. The aforementioned coupled eigensystem can be solved for a set of 12 eigenvalues and corresponding eigenvectors. The component magnitudes of each eigenvector are used to determine the type of dynamic response an aircraft will be subject to if disturbed from the equilibrium condition. The 5 traditional dynamic modes are short period, phugoid, roll, spiral, and Dutch roll. The exact type of motion for each dynamic mode is detailed in this research's conference paper. Once each eigenvector is matched to a traditional mode, the corresponding eigenvalue determines that mode's properties. A mode with complex conjugate eigenvalues is oscillatory, whereas one with purely real eigenvalues is not oscillatory. The real axis corresponds to the mode's damping, with negative values representing a convergent mode. The imaginary axis corresponds to an oscillatory mode's frequency, with larger values corresponding to higher frequencies. The eigensystem-based dynamic stability analysis was implemented numerically using the aircraft model, central difference of derivative approximations, and other necessary physics algorithms. The results of the dynamic stability study are as follows. Plotting the short period eigenvalues of each aircraft over a range of bank angles and center of gravity or CG locations suggests that the BIRE slightly decreases the baseline's short period damping and slightly increases the baseline's short period frequency. The CG location ranges from 1 foot forward of the nominal location to 0 feet forward of the nominal location, with the largest markers corresponding to 1 foot forward and the smallest markers corresponding to the nominal location. The 4 labeled points indicate at what CG location the aircraft's short period splits into 2 real eigenvalues. Further research is required to understand the physical motion represented by these non-traditional real eigenvalues. During steady level flight, both aircraft have convergent phugoid modes. At a 60-degree banked turn, however, both aircraft have divergent phugoid modes. Comparing the two aircraft suggests that the BIRE decreases the baseline's phugoid mode damping and slightly increases the baseline's phugoid frequency. Plotting the non-oscillatory roll mode's damping rate as a function of CG location suggests the BIRE very slightly increases the baseline's roll damping. The spiral mode damping rates corresponding to a 0-degree bank angle suggests the BIRE decreases the baseline spiral mode damping for steady level flight. The jump in spiral mode damping between a CG forward shift of 0.2 and 0.4 feet suggests the BIRE increases the baseline spiral mode damping rate sensitivity to CG location when banked. The BIRE aircraft's purely real Dutch roll eigenvalues suggest the BIRE produces a non-traditional Dutch roll mode. In contrast, the baseline's Dutch roll mode is convergent and traditional. Again, further research is required to understand the physical representation of the BIRE's purely real Dutch roll eigenvalues. The mode properties resulting from the dynamic stability analysis can then be used to quantify the BIRE's effect on the baseline's handling qualities. The handling quality level of each mode represents the amount of effort a pilot must use to counteract that mode's dynamic response. To attain a certain handling quality level for a dynamic mode, that mode's properties must fall within ranges prescribed in United States military specifications. Each aircraft's handling quality levels are as follows. Plotting each mode's handling quality levels suggests the BIRE has a negligible effect on the baseline's short period, phugoid, roll, and spiral mode handling quality levels. However, the non-traditional BIRE Dutch roll suggests the BIRE decreases the baseline's Dutch roll handling qualities to uncontrollable levels. In conclusion, the objective of this research was to identify and quantify the BIRE's effect on the baseline aircraft's static stability, dynamic stability, and handling qualities. This was accomplished by establishing an aircraft model, deriving a coupled eigensystem for asymmetric aircraft, implementing and solving that eigensystem, quantifying the stability of each aircraft, and exploring the trends in the results. Overall, the BIRE decreased the static pitch, roll, and yaw stability of the baseline aircraft. Regarding dynamic stability, the BIRE had a small effect on the baseline's short period and roll modes, decreased the baseline's phugoid and spiral mode damping, and created a non-traditional Dutch roll mode. These dynamic stability results then suggest that the BIRE is able to maintain the baseline's handling quality levels for all modes except Dutch roll, in which the BIRE makes the baseline's Dutch roll uncontrollable. Further work is required to understand the physical representation of the non-traditional real eigenvalues occurring in each aircraft's short period mode and the BIRE aircraft's Dutch roll mode. The oscillatory nature of the phugoid mode properties, as well as the jumping behavior of the banked spiral mode, could also be explored further. Using the methods developed in this research to study additional flight conditions could also prove valuable. Please refer to this research's full conference paper for more details on the topics briefly summarized in this presentation. Thank you.